Hello everyone, I welcome you all to Physics Wallah, and in this session we are going to discuss a very interesting portion related to our very interesting chapter of organic chemistry, which is the concept of optical isomerism. Now, in the previous session we were discussing about the basics related to optical isomerism. We discussed about the symmetry elements and how you are going to decide which carbon is going to be the chiral carbon. Now in this particular session, the main focus will be on the projections related to organic compounds and how you are going to decide the configuration with respect to their optical activity. Okay, so basically in this session, the first part which we are going to discuss is basically the projection formulas. Next part in this case will be the concept of optical isomerism, in which we are going to discuss about the concept of enantiomers as well as diastereomers, and then we are going to discuss about the configurations which are absolute as well as relative configurations, along with a specific idea of meso compounds. Okay, so let's start the session. Basically, if I talk about the entire concept of this optical isomerism, it's time to discuss about the projection formulas. Now projection formulas is basically how you are going to write down the organic compound. So in case of questions, you may find different type of projections in the organic compounds. Mainly there are four type of projections. First one will be the wedge-dash projection, next one will be Fischer projection, next one will be Newman's projection, and last one will be Sawhorse projection. Now don't worry, basically the part which is Newman projection as well as Sawhorse projection, that part we are going to discuss in case of hydrocarbons. But rest of the two parts, first one is the wedge-dash projection and next one is the Fischer projection, that part we are going to discuss in this particular session. Okay, so what about the first part, which is wedge-dash projection? So there are certain basics which you have to understand, then only we know how to write down the wedge and dash projection. So in this particular case, in this method, the four groups bonded to the chiral center are represented by different means. In this case, you are going to represent two atoms which are connected to chiral carbon, which are in the plane itself, and rest of the two atoms you are going to define that part above the plane and below the plane. So in this case, a normal line represent the bond lying in the plane of the paper or plane of the board. So first part is the simple line which talks about the atoms which are present in the plane itself. Okay, I hope this part is clear. Next part in this particular case, a broken line, or you can say dash part, actually represent bond going behind the plane of the paper or that entire board, you can say, which is below the plane. And next part, which is a solid wedge representation, talks about the bond projected towards you, or you can say projected outwards towards the viewer. So this is the representation related to wedge-dash projection. So these two simple lines talks about the atoms which are present in the plane. This one is below the plane and this one is the above plane. I hope this part is clear. And definitely the carbon is connected with four different groups. Definitely that carbon will be the chiral carbon. I hope this part is clear. This is the first type of projection you can see in the organic compounds. Now, if I talk about the next part, which is a Fischer projection, you are actually defining the entire part in plane itself. But in this case, the projection, the point of intersection of two perpendicular lines is used to represent the chiral center. So in this particular case, you are going to write down a structure like plus. Plus sign is going to be used. Now there is the intersection point, this point, which is the intersection point of a plus. This part actually corresponds to your chiral center. This part corresponds to chiral center. Now, horizontal lines actually represent the bonds projected out of the plane of the paper towards the viewer, definitely. So this horizontal line talks about the atoms which are towards you, and this vertical line, actually talks about the other representation, the bonds projected back of the plane of the paper away from the viewer. So in this particular case, you are representing the entire part in the simple plane, but the meaning is different. The horizontal part is towards you and the vertical part is away from you, which is behind the plane. I hope this part is clear. I hope this part is clear. So if I am representing something like that, this is the representation. So this group is, let's say, A, this is B, this is E, this is F. And this intersection point is basically the chiral center. So these are towards you and these are away from you. I hope this representation is clear to everyone. Now, if you look at this entire part, this is exactly the same type of representation. And you can see that this carbon, center carbon, the intersection point is connected with CH3, OH, C2H5H. All the 4 atoms are different. Definitely, that part is going to be the chiral center. So, it's going to show the mirror image. In mirror image, if you want to show, you can only change the position of the horizontal part, because vertical part is going to remain as it is in the mirror image, which shows that you have created 2 different type of molecules which are actually mirror images of each other. But if you want to superimpose these 2 parts, you are going to be like this entire superimposability is not there, because there is a change in the position. If you want to superimpose like that, you can find this OH will be here and this H will be here. So they are not going to superimpose with each other. Definitely both the parts are optically active in nature, and they are generally known as enantiomers. I hope this entire part is clear. Okay. Now, if I talk about the Fischer projection formula, in that case, you can say that Fischer projection of a stereoisomer must not be lifted from the plane of the paper and turned over. Such an operation would result in an arrangement which is enantiomer of the original stereoisomer. So there are certain operations which are allowed, and there are certain operations which are not at all allowed. For example, if I want to talk about this entire part, we have W, Y on the vertical line and X and Z on the horizontal line. If I want to lift and turn over the entire part, it will become like this, because I am changing, like it's going to be turned down like that. So you can see W and Y will remain as it is, and this X and Y, they are going to change its position. It's like the mirror image. It's like the mirror image. So this A part is the enantiomer of this entire part. So you can say you can create a mirror image which are non-superimposable to each other, and you can easily create enantiomers in this particular scenario. I hope this entire part is clear. It's a very simple thing. Don't worry. We are going to discuss about the configuration. Then we can learn how to do all these things with the help of certain specific rules. Okay. Now, Fischer's projection can be rotated in the plane of the paper about the chiral center through 180 degree or its whole number multiple. So the operation which is allowed, you can actually rotate the entire molecule about 180 degree, which is allowed, but you cannot rotate it at 90 degree because it's going to change its configuration. Okay, such an operation produces the same type of arrangement. For example, let's say we have a W here, Y here, X here and Z here. I am rotating the entire part at 180 degree. How I am going to say that? Let's say I have this entire part, I am rotating the entire part at 180 degree. So W will be here and Y will be here. Now in this case, Z will be here and X will be there. So these 2 parts are exactly same. These 2 parts are exactly same. It means you can entirely rotate the molecule by 180 degree, or you can do 2 rotations, 90 degree 2 rotations. You can change this part, you can change this part. These type of arrangements are actually eligible because they are going to create same type of moiety. Okay, I hope this part is clear. This is the most important rule. This is the most important rule. Okay. In the same way, if I talk about the next part, that Fischer projection should not be turned the plane of paper through 90 degree angle. So in case of 90 degree angle, you cannot do that operation in odd numbers, that 1 time 90 degree or 3 times 90 degree, because it's going to create different type of structure. For example, if I'm rotating the entire part by 90 degree only, so you can see that W will be here, X will be there, Y will be here and Z will be here. Now in this particular case, definitely you are changing the entire configuration. If you learn, like if you know how to write down the configuration, then you will know that this type of arrangement is going to create different type of configuration. So that part is not allowed because you are creating an enantiomer. I hope this part is clear. So again, this point is very, very important from the point of view that you want to write down the configuration only. Okay. Now, keeping one group as a steady and the other groups in the Fischer projection can be rotated clockwise or anti-clockwise simultaneously. Such operation would give same arrangement as the original part. So keeping one atom as constant, what you are doing? You are changing one part here and next part here. So you are making 2 changes, 2 type of rotations, 90 degree and 90 degree, which creates 180 degree rotation. That is allowed. That is allowed because it's going to create same type of arrangement. You will learn about the entire part, how these operations are going to work, if you know how to write down the configuration. So that part we are going to cover in this particular session. Okay, so again, this point is a very important. All these points are actually very important when you want to write down the the absolute configuration, not the relative one. Relative is slightly different. Okay, I hope up to that part everything is clear to everyone. These are the 4 important points related to Fischer projection. In the same way, if I talk about the concept of enantiomers, now we can say that we have a chiral center. I can use any of the notation. I can use wedge-dash projection, or I can use Fischer projection. But how to write down its mirror image? It's very easy. So first of all, you can see that we have 2 atoms which are in the plane. So if you want to write down the mirror image, they are going to come on this side. So COH and CH3. Now this above the plane atom will become below the plane in the mirror image, and this below the plane atom becomes above the plane in the mirror image. So you can see it's going to create like this. I hope this entire part is clear to everyone. So you can say the non-superimposable mirror images stereoisomers are known as enantiomers. So they are not going to superimpose with each other definitely, and these parts are actually known as enantiomers. Both are related to chiral carbon only. If this is not the chiral carbon, you cannot talk about the concept of enantiomers. I hope this first part is clear. In the same way, if I talk about the basic characteristics of enantiomer, I can simply say that enantiomers have same physical properties like their melting point, boiling point, density, refractive index, because in this case their molecular formula as well as their structural formula is absolutely same, but their 3-dimensional orientation is slightly different. So their physical properties, they are going to remain same. But enantiomers are optically active substances. Definitely they rotate the plane of polarized light in opposite directions but in equal extent. So if I talk about this example, let's say this is the example. If this entire part is moving the plane of polarized light in the positive direction, and the angle of rotation in that case is, let's say, 70 degree, the second part is going to rotate the plane of polarized light in minus 70 degree. So the amount is going to remain same, but one part will be clockwise, one part will be anti-clockwise. I hope this entire part is clear. These 2 points are related to the basic properties of enantiomers. Just have a look at it. Just have a look at it. Now, the next part is the non-superimposable orientations are non-identical orientations, and that's why they are known as isomers. So one part will be dextrorotatory and next part will be levorotatory. So this part is a clockwise rotation. This part is a clockwise rotation, but this part will be anti-clockwise rotation. I hope this entire part is clear. I hope this part is clear. Now you cannot find out that which particular part is going to be dextrorotatory or which part is going to be levorotatory. You have to perform the polarimeter experiment to know about the orientation, in which part which enantiomer is going to show the dextrorotatory and which enantiomer is going to show the levorotatory orientation. Okay, so enantiomers have identical chemical properties also. This means that they form same products as a result of chemical combination. However, their reactivity, that is the rate of reaction with other optically active substance, they are going to be different, because it's like let's say it's like a key lock system. You must have known the enzyme key lock mechanism. If you know that every lock has a specific key, if you are using another type of key, it's not going to open that particular lock. So every lock has a specific set of keys which can easily open that particular lock. So if I'm using the optically active enantiomer and I'm using a substrate which is optically active, then their reactions might differ. Their rate of reaction is going to differ. Let's say if our body is capable to actually recognize an enantiomer which is positive or which is clockwise rotation, and I'm using a negative or dextrorotatory enantiomer, definitely body is not going to respond towards that part, because our body, which is a lock, is not going to use that key to open the entire system. So that's why these are very specific. Definitely their chemical properties are going to be same, because same type of functional groups are there, but if I talk about the rate of reaction, it might differ. I hope this part is clear. I hope this entire part is clear. So these are the basics related to the part of enantiomers. In the same way, enantiomers have different biological properties. For example, if I talk about the positive sugar plays a significant role in animal metabolism. On the other hand, negative sugar does not play any role in the metabolism, because our metabolism, if I talk about the concept of metabolism, again it's like a key lock system. So if I talk about the metabolism, it's going to be actually driven by a particular lock, a particular key, which is a positive sugar. But if I'm using a negative sugar, which is not the actual key of that lock, it's not going to respond. I hope this part is clear. So it's an extensive application, you can say, related to the enantiomers. Okay. In the same way, if I talk about the next part, which is diastereomers, again, in this case, these are your optically active substances, which are neither non-superimposable, they are not going to superimpose on each other, but they are exactly not the mirror images of each other. So basically, the stereoisomers, which are non-superimposable and do not bear mirror image relationship, so they are neither mirror images to each other, nor they are going to superimpose, definitely that part corresponds to diastereomers. So these are entirely different type of arrangements, different type of molecules. For example, if I'm using this entire part, you can see that this OH is here on the right hand side, this OH is on the left hand side. If I'm actually drawing the mirror image, this OH will come this side, this OH will come that side. So these are mirror images of each other, and we have optically active chiral center. Definitely I can say we are talking about the enantiomers. But if you are comparing this entire part, this OH, this OH, now this entire part can be lifted here in the mirror image. Again, you can see these are mirror images of each other. These are mirror images of each other. But if you compare this third with first, these two molecules are entirely different. They are non-superimposable and they are not the mirror image of each other. If you compare second and fourth, they are not same. Definitely these parts are actually your diastereomers. So first and third and first and fourth, second and fourth, second and third, they are diastereomers with each other. I hope this entire part is clear. I hope this part is clear. Now, in the same way, if I talk about the configuration, now it's time to discuss about the configuration, how to write down the configuration, how to understand which part is going to show which type of configuration, because it talks about the direction in which they are going to move the plane polarized light. So in that case, we have two type of configuration. First part is absolute configuration and next part is relative configuration. First part we are going to discuss about the absolute configuration. So basically it is a detailed stereochemical picture of a molecule, including how atoms are arranged in a three-dimensional space. Because we are talking about the actual arrangement, that's why we are talking about the absolute configuration. And it actually helps us assigning the two types. First one is R and next part is S configuration to each chiral center. R is a rectus, which is a right side clockwise rotation. S is the sinister, which is left or anti-clockwise rotation. I hope up to that part everything is clear to everyone. Just have a look at it. Just have a look at it. Okay. Let's talk about the basic analysis of R and S part. Now, this analysis of R and S actually depends upon the type of projection which you are using. You can define this R and S configuration in Fischer projection, as well as you can define this entire part in wedge-dash projection. But the rules to decide this R and S part, they are going to differ in both the cases. So let's try to figure out what is going to be the absolute configuration in each case. So if I talk about the first part in case of a wedge and dash structure, the idea is very easy, very easy. First of all, decide the priority order of groups by sequence rule, and the sequence rule is nothing but CIP rule, which we already know from E and Z type of configuration. Next part, bring in the lowest prior group to the dashed wedge by the means of a simultaneous exchanges. Now you know that two exchanges they are allowed, but one exchange, this part is not allowed. Or you can say that even changes they are allowed, but odd changes they are not allowed, because they are going to change the entire configuration in that particular case. Okay, now draw an arrow from the first priority group to the second and third priority group only. If the direction of the arrow is clockwise, then it is R. If it is anti-clockwise, then definitely it is S. I hope this part is clear. Now let's try to solve certain questions related to the entire part. Okay, first of all, if I want to look at this entire molecule, I can say that first priority group is already present here, Br. Second is the CH3, H and O. So second will be this O. Third will be CH3 and fourth will be H. Now you can see that lowest priority group is already present on the dash side, which is a good thing. So lowest priority, you can say the lowest priority is already on dash. So you need to make sure that you have lowest priority group on the dash projection. Now if you see that 1, then 2, then 3, it is clockwise. It is clockwise rotation. And clockwise rotation means we are talking about the R configuration. I hope this part is clear. I hope this part is clear. Now you can see again fourth part is present on the dash position. But 1, 2 and 3, this part is anti-clockwise. This part is anti-clockwise. Definitely this part is going to be S configuration. Again you can see in this particular part, fourth group is already present on the dash position. So 1, then 2 and then 3. So it is again your anti-clockwise. Again this part is also anti-clockwise. So definitely it's going to be the S projection. You can solve certain more examples. If you have any of the book, you can try to solve these certain examples to understand what is going to happen if you have wedge dash projection, to understand which configuration it's going to have, S or R. Okay. Now, in the case of a Fischer projection, the entire part is slightly different because we have every atom which is present on that plus sign, or you can say plane. Now, the priorities of the group which are attached with the asymmetric carbon atom are assigned by sequence rule. Again, you can use CIP rule. Again, you can use CIP rule. Next part, the lowest priority group is brought to the bottom of the Fischer projection by 2 or even simultaneous exchanges. So simultaneous 2 or even number of exchanges are allowed. So you need to make sure that the least priority group is present on the bottom position, or it is present in the vertical part, bottom vertical part. Now always remember in this case, if you don't know what is going to happen, or if you don't want to change anything, just remember a rule which is VCR and HCS. What is this VCR and HCS? So first of all, V means vertical position of least priority group. Vertical position of least priority group, and the rotation in this case is clockwise. Let's say it is clockwise. Then configuration will be R. And next part I already told you, that will be HCS. If the least priority group is present on the horizontal part. Horizontal position of least priority group or atom, whatever it is. And again you have clockwise direction according to CIP rule. The configuration will be S. So always remember, if you don't want to change anything, you can remember this entire part. I hope this point is clear. But if you want to make changes, then you can use these rules. Then the arrow is drawn from the first priority group to the second and to the third. If the arrow is clockwise, then we have the R configuration. If it is anti-clockwise, then we have the S configuration. Let's try to figure out together what is going to happen in each and every case. So let's say here I am showing the arrangement. You have to change the position. But if you don't want to change the position, let's say we have this type of arrangement. We have CH2OH, we have a Cl, we have CH3 here, and this must be Br. So first of all, First priority according to atomic number, second priority atomic number. Now these two carbon atoms are there, but here it is connected with 3 hydrogen, here it is connected with 2 hydrogen and 1 oxygen. So third priority will be here and fourth priority will be here. Now the least priority group is present on the vertical line. So VCR. I am going to use this part without any change. So I can say 1 to 2 to 3. So 1 to 2 to 3. It is anti-clockwise. If it is vertical and the rotation is clockwise, it should be R, but it is anti-clockwise. It is anti-clockwise. So definitely that configuration will be S. If you don't want to do anything, if you don't want to do even number of changes, then you can directly use this entire part. I hope this portion is clear. Just have a look at it. So it must be, if this is VCR, so vertical anti-clockwise S. So it should be VAS. Okay, remaining part is going to be same. Vertical, if it is clockwise, then R. If it is anti-clockwise, then definitely it is S. Now, if I talk about this second example, again you can see we have a 1, 2, 3 and 4. So what I do? 1, 2, 3. You can see this direction is again anti-clockwise and this group is present on the horizontal position. So we know that horizontal clockwise is S. So if horizontal anti-clockwise, it should be R. So you can say without anything, I can say that will be R. So finally you can see it's coming like R. It's coming like R. You can see R. So without any changes, you can see R. In this case, again we have a 1, 2, 3. So 1, 2, 3 means it is clockwise and the least priority group is present on the vertical position. So we know that will be VCR. So without anything, I can say it is clockwise rotation. You can see it's clockwise. So definitely it's going to be R. And final answer is R. I hope this part is clear. So it's a simple trick. If you don't want to do the changes, then you can use this entire part. But for wedge and dash projection, you have to make sure that the least priority group is present on the dash position. Then you can see clockwise or anti-clockwise rotation. If clockwise, then definitely R. Anti-clockwise, it must be S. I hope this entire part is clear. Just have a look at it. Okay, now it's time to discuss about the relative configurations. So the relative configuration is with respect to a particular type of standard. In this case, that we have a DL type of system. Relative system means we have capital D and capital L. It's not dextro-rotatory or levo-rotatory, because that is small d and small l, or positive or negative. That type of system is different. That is related to the plane of polarized light, the rotation of plane of polarized light. So always remember, this type of arrangement is related to the rotation of plane polarized light. But in this case, capital D and capital R system are basically the relative configuration. Now in this case, we need a particular standard. We need a reference standard by which I can compare that it's going to be D or it's going to be L. So it is decided on the correct Fischer projection formula only. So this is only applicable in case of a Fischer projection formula. And this method is used to relate the configuration of sugars and amino acid to the enantiomers of glyceraldehyde. So this is our standard reference, which is glyceraldehyde. I hope this part is clear. It's a very important point. So the most useful one will be R and S definitely, but if I am considering sugars as well as amino acid, then I can use their relative configurations also. Now in this particular case, if I talk about the configuration of a plus glyceraldehyde, it has been assigned as D, and the compounds with the same relative configuration are also assigned as D, and those with minus glyceraldehyde, they are assigned as L. But what is this plus glyceraldehyde and minus glyceraldehyde? That thing we have to find out. So in case of glyceraldehyde, if I talk about the formula, it is nothing but CH2OH, then CHOH and CHO. That is glyceraldehyde. Now if you see the position of this entire part, if this OH group is present on the right hand side, if it is present on the right hand side, you can say it is D or plus glyceraldehyde. If it is present on the left hand side, you can say that will be L or minus glyceraldehyde. Now I need to make sure that we are considering these sugars or amino acid. So I need to look at the position of the OH only. Okay. Now the D refers to the arrangement in which OH group attached to the chiral center is on the right side of the Fischer projection, and L refers to the arrangement in which OH group is present on the left side of the Fischer projection of glyceraldehyde. That part is already clear. That part is already clear to us. But in case of sugars and amino acid, how we are going to find out? That part we have to learn. Now this method was found suitable for the study of optically active sugars, as the sugars are defined as polyhydroxy aldehyde and ketones. Now you need to make sure that in case of sugars we have multiple chiral centers. So which chiral center I have to choose? That is the most important part. But remember, in this case I am using the configuration to decide the configuration of sugars, which are basically polyhydroxy aldehyde and ketones, because they contain multiple number of OH atoms. So which OH atom I have to choose? That is the most important question. So in this particular case, glyceraldehyde also contains hydroxyl group and aldehyde group, but this method cannot be used for those molecules which do not possess any hydroxyl aldehyde groups. If you do not have that part, then there is nothing for the comparison, because you need a reference standard, and that reference standard actually contains aldehyde as well as OH group. So you need to make sure that the molecules which I am comparing should also have this OH and CHO group. I hope this part is clear. In the same way, if two or more than two OH groups are present, then D and L configuration is decided on the basis of OH group of lowest chiral carbon. This is the most important point. Most important point. This is the most important point. So that's what I was saying, that if you have multiple OH groups, then how to decide? So in that particular case, you need to look at the lowest chiral carbon and the position of OH. If it is present on the right side, definitely D. If it is present on the left side, definitely L. I hope this entire part is clear. Just have a look at it. Just have a look at it. Okay. Next thing is related to the golden rule. Basically, the Fischer projection is drawn so that the longest carbon chain in the molecule is actually vertical with the highly oxidized functional group at the top. You need to make sure, this is the most important part. You cannot use any type of Fischer projection. You need to make sure that the carbon chain, which is longest one, should contain maximum number of chiral carbons, and the highest oxidized functional group should be present on the top side. Then only you can apply this entire part. It's a very important rule. It's a very important rule. Okay. Now in this case, if I talk about the entire part, this is the form. You can see highest oxidized group present on the top side. OH is present on the right hand side. Definitely D form. In this case, we have multiple OH groups, but the highest one is present on the top side. So I need to look at this chiral center, which is the lowest chiral center. OH is present on the right hand side, D form. OH is present on the left hand side, L form. Now it's clear to you. I guess now it's clear to you. But I suggest you to practice at least 10 to 15 questions related to R and S configuration as well as D and L configuration, so that you can get familiar with the entire analysis. They are very important for from exam point of view. Either NEET exam or JEE exam, they are pretty much required. Okay. Every time you can see at least one question related to the absolute as well as relative configuration of organic compounds. Okay. Now, in case of DL and NIMing for more than one chiral center, so sugars have several asymmetric carbons. It means they have different type of chiral carbons. A sugar whose highest number chiral center, the penultimate carbon, has the same configuration as D glyceraldehyde, definitely OH is present on the right hand side. It is designated as a D sugar, and one whose highest numbered chiral center has the same configuration like L glyceraldehyde, definitely you can say that will be L sugar. So same type of rule is there. You just have to look at the highest chiral center, which is away from the oxidized group. Okay. So in this case, if I talk about this entire part, most oxidized group is present on the top, most oxidized group is present on the top, most oxidized atom is present on the top. Now I can see the highest chiral center, which is far from this group, is on the right hand side. Definitely it will be D configuration. It will be D configuration. You can see it will be D configuration. In this case, it is present on the left hand side. You can say yes, it is L configuration. In this case, it is present on the right hand side. You can say yes, definitely it's going to be D configuration. But the name of the sugar is going to change definitely. That depends upon the number of carbon atoms. So that will be glucose, D glucose and L glucose, and that one will be 3-ose. I hope this entire part is clear. Just have a look at it. Just have a look at it. Okay. Now after completing this entire part, again you can see highest oxidized group is there. This is a ketone. Now in this case, OH is present on the right hand side, definitely D. On the right hand side, again you can see D. Okay, so I hope this entire part is clear. I hope this entire part is clear. So that's how you can deal with these type of configuration. They are very easy to understand. If you know the configuration of glyceraldehyde, it's very easy to understand the entire part. Okay. Now, if I talk about the next part, so just like diastereomers, just like enantiomers, we have a specific set of compounds which are known as meso compounds. So again, meso compounds are like the compounds which have multiple chiral centers. But the case is, these type of compounds have internal type of plane of symmetry which can divide the molecule into two equal halves which are mirror images of each other. So the compounds containing two or more chiral center but possessing achiral molecular structure because of having a plane of symmetry in their structure itself, these are actually known as meso compounds. A very interesting analogy. A very interesting analogy. But the thing is, you should have at least two chiral center. At least two chiral center. More than two, they are very good. But if you have at least two chiral center, but the molecule itself possess a plane of symmetry, then you can say we are talking about the compound which are meso compounds. For example, if you look at this structure, this carbon and this carbon, both are chiral. But if you break down the entire molecule in two equal halves, you can see Br mirror image, H mirror image, CH3 mirror image. Definitely that compound will be meso compound. That compound will be meso compound. Can I talk about their absolute configuration? Yes, very easily. So if I want to talk about this carbon, I can say first group will be this. Now in this case, we have carbon. This carbon is connected with this carbon is connected with this carbon, but this carbon is connected with Br. So that will be the second group, that will be the third group, and this one will be the fourth group. Fourth group is present on the horizontal side. So I can say that we have HCS. Now 1, 2, 3. So I can say 1, 2, 3. Clockwise rotation. It's a clockwise rotation. Fourth group is present on the horizontal. Horizontal clockwise S. So you can say that will be S. That will be S. Definitely S. Okay. Now next part. I'm removing this entire part so that like you can note down the second portion, like how I'm going to decide the priority in second case. In second case, you can say that this group will be the first group, this group will be the second group, and this group will be the third group. And again, fourth group is present on the horizontal side. Now 1, 2, 3, you can see 1, 2, 3 anti-clockwise, horizontal anti-clockwise, horizontal anti-clockwise will be R. So you can say that will be R. I hope this part is clear. I hope this part is clear. Okay. So this compound is meso compound because it has internal plane of symmetry. It has internal plane of symmetry. So you might ask one question, sir, it has a two chiral center. Is it optically active or optically inactive? So first of all, meso compounds are optically inactive. They are optically inactive. But the question might arise, sir, it has chiral center. Why it is optically inactive? So my answer is, You can see this part is R, this part is S. First part is going to rotate the plane of polarized light in clockwise direction. Another part is going to rotate the plane of polarized light in the anti-clockwise direction in the same amount. So the entire change will be 0. Or next part, it has internal plane of symmetry. So if we have a plane of symmetry, the compound will be inactive, optically inactive. So you can say it is optically inactive due to internal plane of symmetry, and this entire part is also known as due to internal compensation. Due to internal compensation, it's going to be optically inactive. I hope this part is clear. Just note down this important point. Just note down this important point. Okay. Now, if you look at this structure, you can draw one plane including CH2. Now, this OH has same mirror image of OH, CH2, CH3 has same mirror image, CH2, CH3, H has same mirror image of H. Again, you have plane of symmetry. Definitely, this compound will be your meso compound. I hope this entire part is clear. I hope this part is clear. Okay. Now, meso compounds do not rotate the plane of polarized light in any direction. It means they are optically inactive. And we know the reason. This is because of achiral nature of their molecules. And because of the presence of plane of symmetry, the optical rotation caused by the first half of the molecule is compensated by the next half of the molecule. And this part is known as internal compensation. This part is known as internal compensation. So it's not necessary that if a molecule contains chiral carbons, it's going to be optically active. If it has internal plane of symmetry, definitely it is optically inactive. I hope this entire part is clear. I hope this part is clear. This is the basic idea about the meso compounds. Okay. For first step practice, I can suggest you to practice certain questions from NCERT itself. Try to write down the relative as well as their absolute configuration from exercise only. And if you want to practice certain more questions, you can refer to PW modules, or if you have any other reference book, that will work. Okay, just try to solve at least 15 to 20 questions from each part so that you get a better understanding. If you have any doubt, if you face any doubt, any difficulty related to R and S as well as D and L, you can ask me in the comment box. I'll try to make sure that you have enough questions and you practice enough questions to understand what is the actual analysis of R and S as well as D and L configuration. Okay, I hope this entire part is clear. Now, if you talk about the cancellation of the rotation within the molecule referred as internal compensation, which I already told you. In short, these meso compounds are optically inactive due to internal compensation. So these 2 points are now clear to you. Okay. Now you can see certain other examples. You can see this is the plane. If I want to draw, definitely first half is having exact mirror image of the second half. Meso compound, in this case, if you draw this line, you can say internal plane is there, Cl, Cl, Me, Me, internal compensation. In this particular case, if you draw this entire part, you can see this is CH, this CH group having H, H, OH, OH, again internal compensation. And this part, if I'm choosing this plane, if I'm choosing plane containing these atoms, so Cl, Cl, Me, Me, H, H, again meso compounds. I hope this entire part is clear. I hope this part is clear. So we discussed about each and everything related to the internal compensation. We discussed about the configuration which are related to the different type of optical isomers. And if I talk about the next part, there is a specific portion which is related to racemic mixture. That part we are going to discuss in hydrocarbons, what are actual analysis of racemic mixture, although that part is very easy in case of racemic mixture, because we are talking about two enantiomers which are present in equal amount. If two enantiomers, let's say we have plus configuration, or you might say small d, and next part is a small l, both are present in equal amount, that mixture is actually known as racemic mixture. that part, racemic mixture, as well as the number of optical isomers, that part we are going to discuss in the next portion of hydrocarbons. Okay, don't worry, we are going to cover that part also, but that part will be covered in the hydrocarbons, because it's better to understand the entire part with respect to certain examples which are relevant to the examination. Okay, that part we are going to cover in the hydrocarbons. Okay, so this is all about the concept of optical isomerism. Just try to stick to the basics. You have to understand what are symmetry elements, and two elements are there, POS, plane of symmetry, and COS, center of symmetry. If they are present, definitely molecule is optically inactive. If we have chiral carbons also, it might be the case that the molecule itself has internal plane of symmetry. Definitely that part also corresponds to optical inactivity. So that is the entire part related to the concept of optical isomerism. So from the next class onward, we are going to discuss the quantitative as well as qualitative analysis of organic compound, and after completing that part, the first portion of organic chemistry will be covered, that is purification as well as estimation of organic compounds. That is your first part of organic chemistry, and next part will be the concept of hydrocarbon. That part we are going to start after completing the quantitative as well as qualitative analysis. Okay, so I hope everyone enjoyed this session, learned something new from this session, and I suggest you to practice at least 15 to 20 questions related to the configuration part. If you find any difficulty, just let me know in the comment box. Okay, I'll try to solve that entire part. Okay, so that's all from my side. Thank you so much.